Given a cylinder with radius r and height h, we're told that the total surface area of the tin is 300 pi and asked to express h in terms of r. I've got to say, I'm not a fan of this question. I think it could have been clearer because, okay, it says it's open, which means there's no top. I'm absolutely fine with that. We're going to get the bottom to be pi r squared, and then we're going to get the outside. But when it says the total surface area, how do I know it doesn't mean the inside of the tin as well? That's part of the surface area. Um, Now, normally you don't, and in this case you don't either, but I feel like it should have said the total outside surface area if I'm being critical, which I am. So let's work out the outside. Imagine taking this cylinder and unwrapping it. It would actually become a rectangle. It would have height h, and the length of the rectangle would actually be the circumference of the circle, so 2 pi r. And that means it's pi r squared plus 2 pi rh, that curved part, that is going to equal 300 pi. Right, now I can actually just divide through by pi. I'm going to do that straight away. And then 2rh is going to equal 300 minus r squared, which means h is going to be 300 over 2r minus r squared over 2r. I'm just going to simplify it. It will become 150 over r minus r over 2. In part 2, it then says, hence show the volume can be expressed like this. Okay, the volume is going to be the cross-sectional area, pi r squared, multiplied by the length, h. And now I can substitute my h in because you can see we're asking for the volume just in terms of r. So 2 pi r, pi r squared times 150 over r minus r over 2. And that will become 150 pi r because the divided by r and the r squared are going to combine to give just r. And then pi r squared times minus r over 2 will give me minus pi r cubed over 2, which is what we need. Finally, using calculus, find the values of r and h for which the volume of the tin is a maximum. So what we've shown is that the volume is a function of r, and as r varies, v will also vary. Now at some point it will hit a maximum value, and that is what we're interested in. It's going to be where the derivative is equal to 0. So let's find dv by dr and set it equal to 0. It's going to be 150 pi minus, and differentiate this, the r cubed is going to differentiate to 3r squared. Actually, all the rest are just constants. So pi times 3r squared over 2. And then that is going to equal 0 with stationary points. So 150 pi will equal 3 pi r squared over 2. Cancel out the pi's. 300 is going to equal 3r squared. Divide through by 3, that make it 100. So r is going to be 10. You can ignore the minus 10 because it's not a physical solution to this. It's got to be greater than 0. R greater than 0. I'm just going to say r greater than 0, so reject r equals minus 10. And then I'm going to find h. H is equal, when r is equal to 10, h is going to equal 150 over 10 minus 10 over 2, which becomes 15 minus 5 is also 10. R is 10, h is 10. The only thing I've not done is shown that it's actually a maximum. So we just need to do that. And we can use the second derivative. So the second derivative is going to be, when I'm differentiating this, the 150 pi is just a constant, so it disappears. The r squared differentiates to 2r, so I'm going to get minus pi times 3 times 2r over 2. The 2's are going to cancel. I'm left with minus 3 pi r. When r equals 10, the second derivative is going to equal minus 30 pi. I don't even need to work out what that is. You can if you want. It's definitely going to be less than 0. And this is enough to say that this implies a maximum. So if you have a stationary point, and then you look at the second derivative, it's less than 0 at the point, it's a maximum. If it's greater than 0, it's a minimum. If it's equal to 0, then you have to do a different test. You have to look into the first derivative instead. You could get a point of inflection, but you could still get a maximum or minimum. I'm not going to go into more detail on that, but just look into that if you've forgotten it. But the first scenario is always to look at the second derivative, and it works out okay here. Well done.